Hello everyone, this is group 2 and in this tutorial video, we are going to discuss about scalar and vector, parallelogram method, head and tail method, component method, motion, and 3 ways of describing motion.
So, good day everyone, I am Corpuz and I'm going to tackle about scalars and vectors. So, physicists, air traffic controllers, and video game creators all have at least one thing in common, vectors. So, what exactly are they and why do they matter? To answer, we first need to understand scalars. So, a scalar is a quantity with magnitude. It tells us how much of something there is, the distance between you and a bench, and the volume and temperature of the beverage in your cup are all described by scalars. Some wild vector quantities also have a magnitude, plus an extra piece of information, which is the direction. To navigate to your bench, you need to know how far away it is, and in what direction, not just the distance, but the displacement.
Good day everyone. My name is Jerome Earl M. Aguirre, and the topic that I'm going to discuss is all about motion. So what is motion? Motion is basically the action of changing position. It is when an object changes its position from one location to another. Now, how do we describe motion? Precise definition for describing motion are speed, velocity, and acceleration. Speed is the rate of which an object moves. Velocity is speed and direction. Acceleration is any change in the velocity.
So this is the game that we created. So this game will demonstrate the 3 ways of describing motion. So first, motion. Motion is the change of an object's position from one location to another. Next is speed. Speed is how fast the object moves. Our player here has a speed of 4. Next is velocity. Velocity is speed and direction. Like for example, when our player jumps horizontally. Our player jumps with direction. Next is acceleration. So acceleration is the change of an object's speed. So when the player collides with the green box, its speed will become times 2. Like for example, our speed is 4. When I touch the box, its speed will become 8. And after 2 seconds, its speed will revert back to its normal. And that is called the acceleration. That's it for our simple game that shows 3 ways of describing motion.
So next, I'm going to tackle about the head-to-tail method. Firstly, I'm going to describe head-to-tail method. So head-to-tail method, this method has advantages in being easy to apply, especially when multiple vectors are to be summed. To sum vectors using this method, simply move them such that the head of one vector is attached to the tail of the other. Let me give you an example. So let's suppose that this is vector A, and this is vector B. So, using the head-to-tail method, we're just going to attach the head of vector B to the vector A to the tail to the head of vector A. Oh. There. So to get the resultant vector, starting from the initial position to its final position, that's where we can get the resultant vector. there. Next, we're going to talk about parallelogram method. So, parallelogram method, it is if two vectors acting simultaneously at a point can be represented both in magnitude and direction by the adjacent sides of a parallelogram drawn from a point. Then the resultant vector is represented both in magnitude and direction by the diagonal of the parallelogram passing through that point. So, let me give you an example. Supposedly this will be vector A and this will be the vector B, and see how to use parallelogram method. Next, I will show you how to use the component method and give you examples. So, the objectives is first, is to learn how to use the component method in a Pythagorean approach. Next is to learn to add 3 or more right angle vectors and learn how to use SOHCAHTOA to get the direction of vectors. So, we already learned that vectors oriented at right angles to one another can be added together using the Pythagorean theorem. For instance, let's suppose that these two displacement vectors with magnitude and direction of 11 kilometers north and 11 kilometers east can be added together to produce a resultant vector that is directed both north and east. So when the two vectors are added head to tail as shown, the resultant is the hypotenuse of a right triangle. The sides of the right triangle have lengths of 11 kilometers and 11 kilometers. So the resultant can be determined using the Pythagorean theorem. So so we can see now that it has a magnitude of 15.6 kilometers. So this Pythagorean approach is a useful approach for adding any two vectors that are directed at right angles to one another. So a right triangle has two sides plus a hypotenuse, so the Pythagorean theorem is perfect for adding two right angle vectors. So next, I'm going to show you how to add 3 or more right angle vectors. So I'll give you first an example. So, Isronet and Jerome are doing the vector walk lab. Starting at the door of their physics classroom, they walk 2 meters south. They make a right-hand turn and walk 16 meters west. They turn right again and walk 24 meters north. Then they turn left and walk 36 meters west. So, what is the magnitude of their overall displacement? So a graphical representation of the given problem will help visualize what is happening. So the diagram shown depicts such representation. So when these 4 vectors are added together in a head-to-tail fashion, the resultant is a vector that extends from the tail of the first vector, so 2 meters south, shown in red, to the arrowhead of the 4th vector, 36 meters west, shown in green. The head-to-tail vector addition diagram is now shown. So the resultant vector drawn in black and labeled R in the vector addition diagram that is shown is not the hypotenuse of any immediately obvious right triangle, but by changing the order of addition of these 4 vectors, one can force this resultant vector to be the hypotenuse of a right triangle. For instance, by adding the vectors in the order of 2 meters south plus 24 meters north plus 16 meters west plus 36 meters west,
the resultant becomes the hypotenuse of a right triangle. So this is now the addition diagram. So with the vectors rearranged, the resultant is now the hypotenuse of a right triangle that has two perpendicular sides with lengths of 22 meters north and 52 meters west. The 22 meters north side is the result of 2 meters south and 24 meters north added together. The 52 meters west side is the result of 16 meters west and 36 meters west added together. So the magnitude of the resultant vector r can be determined using the Pythagorean theorem. So here is the solution. SQRT indicates square root. So as can be seen in the example, the resultant of the addition of 3 or more right angle vectors can be easily determined using the Pythagorean theorem. Doing so involves the adding of the vectors in a different order. So now, I'm going to show you how to use SOHCAHTOA to determine the direction of vectors. So let's use the example 1, wherein we made an effort to add 3 vectors, 6 kilometers north plus 6 kilometers east plus 2 kilometers north. So in the solution, the order of addition, the 3 vectors was rearranged so that a right triangle was formed, with the resultant being the hypotenuse of the triangle. So the triangle is redrawn at the right. So observe that the angle in the lower left of the triangle has been labeled as theta. Theta represents the angle that the vector makes with the north axis. So theta can be calculated using one of the 3 trigonometric functions, which is the sine, cosine, or tangent. Or the mnemonic SOHCAHTOA is a helpful way of remembering which function to use. So in this problem, we wish to determine the angle measure of theta, and we know the length of the side opposite theta. So here it is. So tangent is equals to opposite over adjacent. So our tangent is equal to 6 divided by 8. Then the result was 0.75. So tan 0.75, 36, which is overall 37 degrees. So the problem is not over once the value of theta has been calculated. This angle measure must now be used to state the direction. One means of doing so is to simply state the direction of the resultant, which is 37 degrees east of north. Alternatively, the counterclockwise convention could be used, since the angle that the resultant makes with east is the complement of the angle that it makes with north. So we could express the direction as 50 degrees counterclockwise.